In this section, we will discuss terminology associated with a single nephron. The remainder of the chapter is concerned with the renal handling of specific substances, such as sodium, chloride, bicarbonate potassium, and water. One level of understanding can be achieved at the level of the whole kidney function. For example, sodium is freely filtered across the glomerular capillaries, almost completely reabsorbed, and only a small fraction of the filtered load is excreted. However, what are the details of the reabsorption process? Is sodium reabsorbed throughout the nephron or only in certain segments? And what cellular transport mechanisms are involved? To answer these more sophisticated questions, techniques have been developed to study single nephron function. In the micropuncture technique, fluid is sampled directly from individual nephrons and analyzed. In the isolated perfusion nephron technique, segments of nephrons are dissected out of the kidney and perfused with artificial solutions in vitro. In the isolated membrane technique, vesicles are prepared from luminal or basolateral membranes of renal epithelial cells to study their biochemical and transport properties. The terms associated with single nephron function are parallel to those used to describe whole kidney function. For example, U represents urine in whole kidney terminology, and the parallel term for single nephron, TF, represents tubular fluid. GFR represents whole kidney glomerular filtration rate, and SNGFR is the filtration rate of a single nephron. A summary of terms, abbreviations, and meanings is provided in Table 6-3. As you recall, Table 6-3 is located on page 245 of your text. One particular concept that often comes up on the USMLE exam is the tubular fluid to plasma concentration ratio. The tubular fluid to plasma concentration ratio compares the concentration of a substance in the tubular fluid to its concentration in systemic plasma. Using the micropuncture technique, the tubular fluid to plasma concentration ratio can be measured at various points along the nephron, beginning in Bowman space. Plasma concentrations are assumed to be constant, and any changes in the tubular fluid to plasma concentration ratio, therefore, reflect changes in tubular fluid concentration. To understand how the tubular fluid to plasma concentration was applied, consider a simple example. Assume that the tubular fluid to plasma concentration ratio of sodium was measured in Bowman space and found to be 1.0. A value of 1.0 means that the tubular fluid sodium concentration is equal to the plasma sodium concentration. This value makes perfect sense based on knowledge of glomerular filtration and handling of sodium in particular. Sodium is freely filtered across the glomerular capillaries into Bowman space. The sodium concentration of the filtrate should be identical to the plasma concentration with a small Gibbs-Donan correction. No reabsorption or secretion has yet taken place. The generalization can be made that for any freely filtered substance, the tubular fluid to plasma concentration ratio is 1.0 in Bowman space. This is before any reabsorption or secretion has taken place to modify it. The following interpretations can be given for values of the tubular fluid to plasma concentration ratio, where X is any solute. Again, the plasma concentration of X is assumed to be constant. If the tubular fluid to plasma concentration ratio of substance X is equal to 1, it can have two meanings. The first meaning is illustrated in the preceding example. In Bowman space, the tubular fluid to plasma concentration X for a freely filtered substance is 1 because no reabsorption or secretion has yet occurred. The second meaning is more complicated. Suppose that tubular fluid is sampled at the end of the proximal tubule, and the tubular fluid to plasma concentration is found to be 1.0. Does that mean that no reabsorption or secretion of the solute has occurred in the proximal tubule? Not necessarily. It is also possible that reabsorption of the solute has occurred, but in exactly the same proportion as water. If the solute and water are proportionally reabsorbed, the concentration of the solute in the tubular fluid does not change. In fact, this is precisely what happens in the case of sodium. In the proximal tubule, sodium is reabsorbed, but the tubular fluid to plasma concentration of sodium remains 1 along the entire proximal tubule because there is proportional sodium and water reabsorption. A tubular fluid to plasma concentration ratio of substance X of less than 1 has only one meaning. Reabsorption of the solute must have been greater than the reabsorption of water. This causes the concentration of the solute in tubular fluid to decrease below that in plasma. A value greater than 1 has two possible meanings. The first meaning is that there has been net reabsorption of the solute, but the solute reabsorption has been less than water reabsorption. When solute reabsorption lags behind water reabsorption, the tubular fluid concentration of the solute increases. The second meaning is that there has been net secretion of the solute into the tubular fluid. This would also cause its concentration to increase above that in plasma. The previous discussion about values of tubular fluid to plasma concentration ratio emphasizes how their interpretation requires a simultaneous knowledge of water reabsorption. Recall one of the questions asked. Does a tubular fluid to plasma concentration of a substance X equal 1.0 because there has been filtration but no reabsorption or secretion? Or does the tubular fluid to plasma concentration of a substance X equal 1 because there has been proportional reabsorption of the solute and water? These two very different possibilities can be distinguished only if water reabsorption is measured simultaneously. Inulin, the substance used to measure GFR, can also be used to measure water reabsorption in the single nephron. Recall that once inulin is filtered across glomerular capillaries, it is inert. It is neither reabsorbed nor secreted. Thus, the concentration of inulin in the tubular fluid is not affected by its own reabsorption or secretion. It will be only affected by the volume of water present. In Bowman's space, for example, the tubular fluid inulin concentration is identical to the plasma inulin concentration. This is because inulin is freely filtered. As water is reabsorbed along the nephron, the inulin concentration of tubular fluid steadily increases and becomes higher than the plasma concentration. Water reabsorption can be calculated from the value of the tubular fluid to plasma concentration of inulin. Consider an example in which tubular fluid is sampled and the measured tubular fluid to plasma concentration of inulin is equal to 2. In words, this means that the tubular fluid inulin concentration is twice the plasma inulin concentration. Water must have been reabsorbed in earlier portions of the nephron to cause the tubular fluid inulin concentration to double. How much water was reabsorbed to achieve this value of tubular fluid to plasma concentration of inulin? This simple example can be analyzed intuitively. If the tubular fluid inulin concentration doubles, then 50% of the water must have been removed, in this case, reabsorbed. Other values of the tubular fluid to plasma concentration of inulin can be used to measure water reabsorption by the following equation. The fraction of filtered water reabsorbed is equal to 1 minus 1 over the tubular fluid to plasma concentration of inulin. This equation is given on page 265 of the text. The equation can be understood by comparing it with the intuitive solution for a tubular fluid to plasma concentration of 2. In that example, the fraction of the filtered water reabsorbed is 1 minus 1/2, or 50%. The mathematical solution provides exactly the same answer as the intuitive approach, which also concluded that 50% of the water is reabsorbed. Other values of the tubular fluid to plasma concentration ratio of inulin are not as easy to solve intuitively, and then the equation must be used. For example, if the tubular fluid to plasma concentration of inulin is equal to 100, the fraction of the filtered water reabsorbed is 1 minus 1 over 100, or 99%. Incidentally, this is the value of the tubular fluid to plasma concentration of inulin that could occur at the end of the collecting ducts, at which 99% of the filtered water has been reabsorbed back into the blood. The tubular fluid to plasma concentration of inulin ratio provides a tool for correcting the tubular fluid to plasma concentration ratio of a substance X for water reabsorption. With this correction, it can be known with certainty whether a substance has been reabsorbed, secreted, or not transported at all. The tubular fluid to plasma concentration ratio of a substance X divided by the tubular fluid to plasma concentration of inulin is a double ratio that makes this correction. The exact meaning of the double ratio is this: the fraction of the filtered load of the substance X remaining at any point along the nephron. For example, if the tubular fluid to plasma concentration ratio of substance X divided by the tubular fluid to plasma concentration of inulin is 0.3, then 30% of the filtered load of the solute remains in the tubular fluid at that point in the nephron, or 70% has been reabsorbed. This is approximately the situation for sodium at the end of the proximal tubule. The tubular fluid to plasma concentration ratio of sodium over the tubular fluid to plasma concentration of inulin is equal to 0.3. This means that 30% of the filtered sodium remains at that point, and 70% has been reabsorbed. From the earlier discussion, recall that at the end of the proximal tubule, the tubular fluid to plasma concentration of sodium itself is 1. This led to the confusion about whether sodium was reabsorbed in the proximal tubule. Now, using the double ratio to correct for water reabsorption, the answer is clear. A large fraction of the filtered sodium has been reabsorbed, but since water is being reabsorbed along with it, the tubular fluid to plasma concentration of sodium does not change from its value in Bowman's space.